Welcome back, everyone. We are getting to the first part of chapter 11.2, and we're going to be talking about series. Series is when we take a sequence, A sub n, and we add up all of the elements. Now, if we end up with the ellipsis at the end here, that means we have what's called an infinite series. And for the rest of this chapter, we will be mostly interested in only infinite series. But we can have a finite series. For example, this one goes from 1 to n as we're looking at it. So let's go through a definition. So here we have a summation of all the sequences. And if we stop at n, meaning it doesn't go off to infinity, then it's called the nth partial sum. That's what this is. S sub n is adding them up until it ends. Now, if the sequence S sub n is convergent, and the limit goes to L exists. Now remember, L has to be one specific number. So it can't be like plus or minus something or anything like that. It's got to be one specific number. Then we say that the series is convergent. So meaning if I add all this up and then I take n and shove it off to infinity, and it goes to a specific number, then we say that it's convergent. Now, this should seem a little weird to you. This is us adding up an infinite number of numbers, all infinity of them, meaning if we stop at 500 trillion, not enough. We have to add up all infinity of them to hopefully come up with a finite number. Now that should really kind of mess with your head a little. But in reality, we actually do things like this all the time. All right. Now, if it doesn't go to a specific number, then we can say that the series is divergent. And for this chapter and the next several, for this section and for the next several sections, our only job will be to figure out if a series is convergent or divergent. And in some cases, we're going to break up convergent into specific types of convergence. Let's jump on our first one here. So S sub n in this case is here. And if we're adding up all of those, then we'll have to start out with a limit as n goes to infinity. As n goes to infinity of S sub n. So here we go, 2n over 3n plus 5. And what we're going to do is I'm going to factor out an n out of the denominator. Oops, limit n approaches infinity. And we're going to get 3 plus 5 over n times n. I'm going to notice that the n's reduce. And I'll also notice that this limit here goes to 0. And when it's the same degrees like that, we know that that's going to go to 0. So our answer is actually 2/3. So what we're doing is we're taking this infinite series, infinite, we're adding up all of these terms, all infinity of them, and it's going to exactly equal 2/3. Again, that should seem a little strange to you, but there it is. So now I want to talk about a specific test. Now, if you remember when we were doing techniques of integration, we learned a bunch of different techniques. That's kind of what we're doing here. What are different tests that we can run to see if a series is convergent or divergent? Again, that's our goal here. All right, a geometric series has what's called a common ratio. That we call R, meaning if I take any of the terms, any two successive terms, and I divide them out, I should end up with my common ratio. Meaning if I do AR divided by A, I get R. AR squared divided by AR, R. AR cubed divided by AR squared, R. So that is what's called the common ratio, meaning we're going to be multiplying by R to get the next term as we go out there. And the geometric series looks like this. Now I want to point out A is the first term. In the series. So in some cases, we're going to have to be a little extra careful. Now the nth sum is here, meaning if we add up just n of them, we're not doing infinity or anything like that. This is the formula for that. It's not hard to derive. It's actually pretty simple. Now the key is we want n to go off to infinity because we want an infinite series, which is our geometric series in this case. So what happens is, as n goes to infinity, the only part that's affected is right here. It's the only n in the whole formula. Now, the thing is, if n isn't between -1 and 1, this whole thing goes off to infinity, which means it's divergent. We are interested in when is it convergent? Well, if r is between -1 and 1, that part actually goes away completely. And we end up with this formula here. So we can say that a geometric series is equal to a over 1 minus r only when r is less than 1. So let's try it. So I'm going to take any of the two terms and divide them out. So I need r. So I'm going to go -10 over 3 divided by 5. And that actually is going to reduce to a -2/3, right? 10 over the 5, the whole thing's over 3. So we have our r. We also have a. And by the way, our r is between -1 and 1. A in this case is 5. So for our sum, we're going to have 5 over 1. Now be careful, it's going to be minus minus. And here it reduces. We end up with, remember you multiplied by the reciprocal? So we just end up with 3. Once again, I want us to take a look at this series. We are adding up an infinite number of these numbers to exactly get the number 3. Weird stuff. All right, next up, we have our example 3 here. Let's get our common ratio. R is going to be -2 over 10, or -1/5, which again is between -1 and 1. A in this case is 10. Oh, I should mention this previous one, that 3 means that the series converges. I want to make a note real quick that these first few tests that we're going to be running, we actually know what it converges to. Later, we just need to know convergence or divergence. We will not have a way of knowing what they converge to. And there's a reason for that. We don't need to know, actually. So in this case, S is going to be A, which is 10, divided by 1 minus minus again, be careful. 10 over 1 plus 1/5, that's going to be 6/5, which is going to flip around and reduce to become 25/3, which once again is convergent. All right. Next up, we're going to keep going with the geometric series. All right, so here we have a geometric series, and what we need to do is figure out if this is going to be convergent or not. So let's do this. Let's find our first two terms. So when n is 1, that's going to be 2 to the second power times 3 to the 0, right? When n equals 1, 1 minus 1 is 0. So that first term there is 4. When n equals 2, that's going to be 2 to the fourth power times 3 to the negative 1. That's going to be 16 over 3. And let's now find our common ratio. R, 16, not 10, over 3, divided by 4. Which is the same thing as multiplying by the reciprocal. So that's 16/3 times 1/4. We can see this is going to reduce. To 4/3, which is bigger than 1. So this one is divergent. Now I do want to point out, this one doesn't look like our geometric series, so I could actually rewrite this as this. I'm rewriting this here. 2 squared is 4, that's 4 to the n. Times 3 times 3 to the negative n. So this actually becomes this. And I know the formula says n minus 1, that it really doesn't matter. N minus 1 and plus 1, it doesn't matter. But we can see this is our R, our common ratio, which we learned earlier. All right, so let's do the same thing here. Let's find our first term, a sub 1. That's going to give me negative 3 to the 0 power. That's going to be 1/4. So there's my A, if it does converge. Let's see what our second term is and come up with our R. It's going to be negative 4/3. You can kind of see it there. So when A equals 2, that's going to give me negative 3 up top. 2, that's going to give me 16. So our common ratio is going to be negative 3 over 16 over 1/4. And flipping that all around, that's going to give us a common ratio. Let's write it out. 3/16 times the reciprocal, which is 4. So R equals negative 3/4, which is between negative 1 and 1. So we're good to go. A, which is 1/4, divided by 1 minus negative 3/4. So that becomes 1 plus 3/4. That's going to give me 7/4. That's going to give me 1/7. Meaning it is convergent. All right, this last example for this part of the video, example 7 will be part of the second half of the video, is we can actually take a fraction, a decimal, a repeating decimal, and convert it into a fraction. Now, I need a little bit more space here. So what I'm going to do is I'm going to use the back of the sheet here. Let's push that up. So 2.3. Now only the 1/7 is being repeated. So this is actually going to be 2.3 plus 0.017 plus 0. And how many zeros? 1, 2, 3 of them. 1, 2, 3, 1, 7 plus 0.1, 2, 3, 4, 5, 1, 7, and so on. Now the 2.3, that's 2 plus 3/10, which is actually 23 over 10. We'll come back to that. I want to focus on more the repeating part. So this part here, so let's denote that we're just going to be talking about this part here. is actually 17 over 1,000. This is 17 over, so that's tenths, hundredths, thousandths, 10,000, 100,000ths. Over tenths, thousandths, 10,000th, 100,000th, millionth, 10 millionth, 100 million. I'm off by one. I think that's 10 million. Either way, plus. This is going to become 17 over 10 to the third plus 17 over 10 to the fifth plus 17 over 10 to the seventh, and so on. And you'll note if I divide those out, any of those two out, 17 over 10 to the fifth over, this is R, 17 over 10 to the third times the reciprocal, 10 to the third over 17. We can see that reduces, as does this. So we end up with our R is 1 over 100, 10 squared. Well, that's definitely less than 1. So let's come up with the sum. Now this sum is only for here. So once I get that sum, I'm gonna have to add that 23 tenths there. So this is going to be A, here's my first term, 17 over 10 to the third over 1 minus 1 over 100. So this is looking to me that this is going to be 17 over 990. So I now need to add up. So 2.317 with a bar is now 23 tenths plus 17 over 990. And multiplying 99 to the top and bottom here and adding it up, I'm going to get 2294 over 990, which we can reduce a 2 out of that. 1,147 over 495. Now, let's double check that. So let's take 1147 and divide that by 495. Look at that. It's exactly 2.317 bar. Pretty cool stuff. I want to do one more of these for you. This is not in your notes, but I think it's interesting to see. We could use the same logic and do that 0.3333 bar is 1/3. But I want to do this one. .9 bar. Now I want you to think about that. We're not going to do any rounding off. This is 0.9 plus 0.09 plus 0.009 plus and so on, which becomes 9 tenths. So there's my A. 9 over 100, which is 10 squared, plus 9 over 1,000, and so on. A in this case is the 9 tenths. R in this case, 9 over 10 squared over 9 over 10 becomes 1/10. So our sum is going to be 9 over 10 over 1 minus 1 over 10, which becomes 9 tenths over 9 tenths, which is 1. I want you to think about that. 0.9 bar is exactly equal to 1. That should mess with your mind a little. That's the end of part one. Part two is coming up.